Welcome back to Applied Mathematics. In this video, I want to introduce you to the problem-solving strategies for mixture problems. This is actually two very closely related strategies, one for what's known as a value mixture problem and one for a percent mixture problem. Mixture problems are kind of what they sound like. The situation at hand is that we're going to mix things together that have a different value of some way, shape, or form, and look at how the values for the things that we are mixing together inform the value of the resulting mixture. Let me get my head out of the way, and let's jump right in. This is an example of a value mixture problem. A local coffee shop plans to create a house blend coffee by mixing an 18-pound bag of luxury coffee beans, which costs $375, with some amount of a cheap filler bean, which they can purchase for $5.25 per pound. If they want this blend to be worth $12 per pound, how much filler should they use? Somehow the letter Y got dropped off of the word they there. I don't know how that happened. Anyway, this is probably not a problem that anyone in this course is going to directly be working in their life, but I think it's a pretty approachable example of the idea of value mixtures. The value, in this case, the cost value of luxury coffee beans, cheap coffee beans, and the house blend have to be related to each other. Right? When you put beans together, the cost that it takes to purchase the luxury beans that you pour into the mixture and the cost that you spend to get the filler beans that you put into the mixture gives you the total cost of the mixture. That relationship is what tells you you have a mixture problem. And when we have a mixture problem, I tend to approach them using a table. So, we're going to have several columns here. The first column is going to be the type. We have the luxury beans. We have the filler beans. And then we have the house blend. Technically speaking, you could leave this column off of the table, but having this column helps you remember exactly what you're doing, so I think it's worthwhile. Now, for these beans, we actually don't know anything about the value, which in this case is the cost per pound of the luxury beans, but we do know the cost per pound of the filler beans, and we do know the cost per pound of the house blend. We also know some things about the weights. We know that we are using 18 pounds of the luxury coffee beans, and we don't know how many pounds of the filler we're using, but we do know that's what we're being asked for. So filling in there with our variable and calling it x is probably going to be worthwhile. Finally, we know that the total cost of the luxury beans was $375. That's all of the information that was given to us in this problem. And there's a little bit more we could figure out. We could figure out the cost per pound of the luxury beans, but it turns out to not really be valuable in this problem, so I'm happy to leave that blank. The weight of the house blend is very easy for us to calculate. We know that there's 18 pounds of the luxury beans. We know that there's this unknown value that we've labeled as x, pounds of the filler beans. And we know that we're just dumping those two things together. All of the weight of the luxury beans is going into the blend. all of the weight of the filler beans is going into the blend, and there's nothing else going into the blend. So the weight of the blend has to be 18 plus X. Now the big one. The cost per pound that we have is a unit rate. And we know that if we have a cost per pound and we multiply it by a number of pounds, the result will be a cost. So in this case, $5.25 times X is just 5.25X. And then for the house blend, it looks a little bit messy, but 12 times 18 plus X gives us the total cost of the house blend. Now, there's one thing left to do. The total costs. Just like the total weight, right? The weight of the house blend has to either come from the luxury beans or the filler beans. It all has to get there. Nothing else can get there. The same with the total cost. We are making this by putting some amount of money into purchasing luxury beans. We're putting some amount of money into purchasing filler beans, and that's the amount of money that goes into the house blend. There's no other money that we're talking about, so we can't gain any money, we can't lose any money. It must be the case that the total cost of the things we're putting in is the same as the total cost of the thing we get out. That allows us to write an equation. 375 plus 5.25x is equal to 12 times 18 plus x. We can distribute on the right-hand side. 12 times 18 is 216. We can get all of the x onto one side of the equation by subtracting 5.25 from both sides of the equation. 12 minus 5.25 is 6.75. We can get the term with x by itself by subtracting 216. That comes out at something. There we go. Now my calculator is agreeing with me. 159. And then divide to solve for x. I'm going to round it up and call it 23.6. And that is exactly the thing the problem was asked for, right? When we wrote down x, we put it in exactly the spot of the weight of the cheap filler beans. And so we can answer our question. We need to add 23.6 pounds of cheap filler beans to our house blend. There's several question marks that are left here that are a little bit beyond the scope of this problem, right? We had to round that somewhere, and that might not have been the right place. If we are buying our coffee by the pound, it might be that the only valuable way or the only cost-effective way of making this blend is to put a whole number of pound of beans in, because we can only buy 1 pound bags. Or it might be worse, we can only buy 10 pound bags, and we have to adjust our plan. It's over here. we have to adjust our plan of making the house blend worth $12 a pound. But it's a starting point and it lets us continue that conversation. Closely related to a value mixture problem is a percent mixture problem. They're really the same thing, except that instead of having values, the values are percents. This is probably going to be more likely to be something that you run across, but the process is going to be much the same. The chemistry stockroom keeps a 35% ethanol solution on hand. How much of this stock solution must you mix with pure water to create 25 liters of a 10% solution? Once again, this is a mixture problem. We're mixing together a stock solution and pure water, and we're creating a application solution. This is a little bit interesting because we have this pure water that we're going to have to think about. It's also interesting because it is percents instead of numerical values. In one sense, that makes the table a little bit easier to work with, because your labels, your types of things that you're mixing together, give you information. We have a 35% solution, we have pure water, and we have a 10% solution. We're talking about some volumes. So that's probably a place that's worth looking at. Specifically, we want 25.0 liters of our 10% solution. That's the only volume that we are given. And then we have some concentrations. We already wrote these down, so you might not even think of writing them down again, but I'm going to take this opportunity to remember that even though percents look like numbers, they are not actually numbers. In order to actually do anything with these, we're going to need our percents to be rewritten as decimals or fractions, but decimals tend to be a little bit easier. All right, and that's everything that's given to me in this problem. From here, I have to start making some inferences and making some calculations. The inferences require a little bit of knowledge of chemistry, but I think that they are reasonable. I think that middle school science level should get you near to this kind of knowledge. First of all, that pure water has a concentration of 0. Right? Pure water, by definition, has no ethanol in it. And that last thing I said gets to the real heart of the matter. When we are looking at the information that we're given, something that's going to be very useful to us is knowing the amount of ethanol. And right now, we don't have a lot to go on. We do know that we want at the end 25 liters of our 10% solution. And if we take 10% of 25, multiplying these two columns together, we get that there are 2.5 liters of ethanol in our final result. Continuing on a little bit from here. The question is specifically asking us how much of the stock solution we are going to need. So at some point we should go ahead and name that thing as a variable, call it x. And in this particular problem, we don't actually need to know the volume of pure water involved, but it's pretty easy to figure out, and I think it's worth making sure that you, making sure you see how this works. I don't know what the volume of pure water is, but I know that if I add x plus the volume of pure water, I have to get the 25 liters of the solution that we are going to be using. The only way that works is if the volume of pure water is 25 liters minus x. But then from here, I'm going to multiply across. X times 0.35, there's 0.35x liters of ethanol in the 35% solution, in the x liters of the 35% solution. And then the reason I said we didn't need that other volume, I'm going to multiply 25 minus x times 0 to get that there are 0 liters of ethanol in the in the pure water. And again, this bit here is the thing that we can really focus on. I know that I need to end up with 2.5 liters of ethanol. I know that I got no ethanol from the pure water, but I did get some ethanol, 0.35x, from the 35% solution that I included. So, solving this equation for x, not a particularly challenging equation. Although the value I get out is kind of nasty. (7.142857), etc. It's hard to say what is exact and approximate here. I haven't been paying close attention to significant digits, but I guess that for the most part, I have 2 significant digits on a lot of things. So probably 7.1 liters is the best reporting that I can have here. All right, so in this problem, we're going to need 7.1 liters of our 35% ethanol solution, and then the remainder, 25 liters minus 7.1 is 17.9 liters of pure water. Mix those things together, following the appropriate safety protocol of a chemist, and you have your ethanol mixture. All right. It gets a little bit messier, it gets a little bit harder to follow when we talk about percent mixtures, but the process is very much the same, and hopefully this is starting to make sense to you, and you can start to see how this sort of problem solving can appear in a number of other places as well. For now, though, that's all I have for you, so thanks as always for joining me, and I'll see you in the next video.